So, let's talk about a new type of circuit. Alright, so we've sort of talked about capacitors when they're charged and when they're discharged, right? When they're discharged, they have 0 volts across them, there's no charge. When they're charged, they have some delta V and some Q affiliated with them. But does this happen instantly? No, right? So there's going to be some time involved, some time when the capacitor is only partially charged before it becomes fully charged. And you can imagine that the amount of time it takes to charge and discharge a capacitor probably has something to do with the type of capacitor you're using, or the capacitance of that capacitor. Okay? So we're going to use loop law to figure this out. So here we have our change in voltage across the capacitor and our change in voltage across the resistor. So delta C plus delta VR. All right? So it turns out delta VC, if you're going this way, okay, that's going to be negative charge over capacitance. And that's just from the definition of capacitance, right? The definition of capacitance is Q over delta V. So if we solve for delta V, that's going to be Q over C. And why do we use little q in this case? What do we usually mean when we use a lowercase letter?
It's a variable.
It's a variable. It's changing, right? Because as this thing charges and discharges, Q can get bigger or smaller. So this changes. C is capital because capacitance isn't going to change, okay? And then if you go through this resistor, you have a current times R. Delta V equals IR, okay? So this is delta V for the capacitor. This is delta V for the resistor. This is just loop law, okay? And I want you to remember what happens, how do we define current? What's the definition of current?
Flow of charges.
What?
The flow of charges.
Mathematical definition.
V over R. Coulombs per second.
Coulombs per second is the closest. dq dt, right?
Oh, dt.
It's the derivative of charge with respect to time. Okay? What kind of equation is this?
Go.
Well, it will be.
Oh.
What kind of math is this?
Cut.
This is a differential equation. Okay? Fortunately, it's only a first order, so you can solve it with an integral. Okay? Don't stop. Just so here, let's call this. We have dq dt is equal to negative. Let's see. Put that over there. So that's going to be q. So that's rc 1 over rc. That moves over there. Yeah, and that's q. Okay. We're going to separate this. Okay, so we're going to say dq is equal to negative 1 over rc dt. I'm going to bring q over here, so this is dq over q. All right? Now we can integrate both sides. Okay, I ran out of space, but you get the idea. So what's the integral of 1 over x?
1 over natural log.
It's going to be natural logs, right? Okay. Let's say plus c. And this is going to be just negative t over rc, because this is not, these are both constants, you can pull it out, this just becomes dt, so that's t. Okay? It turns out this plus c ends up being the initial conditions. We'll talk about that in a little bit. But if you want to solve this, this becomes plus c. We're just going to ignore this for now. I'll bring it back later. But the e to the this gets q by itself. So q of t is just going to be e to the negative t over rc. It turns out the q comes back here. Okay? So this is discharging. Oh, sorry.
Wait.
Charging. Okay, so you end up with something that looks like this. You don't have to remember this. I'm just showing you where it comes from. So you're not like, well, how the fuck did we get this? Okay, looks like this. Charge on a capacitor in an RC circuit, which changes with time, is equal to the initial charge on the capacitor when it's connected to the resistor, and the time since connected to the resistor. This tau is equal to RC. That's something called the time constant. Turns out resistance times capacitance gives you seconds.
Alright.
Right?
So now tau is RC
Ohms
now.
times farads
So that-
I
equals
thought tau was torque.
seconds.
That E is exponential.
You thought tau was what?
Torque? Isn't tau torque?
Yeah,
Yes,
it
it
is.
is.
But don't worry about that.
So isn't that E is exponential?
Yeah, that's E,
Yay.
like
Physics.
2.73 or whatever E is.
Like okay.
Okay,
Like
so
element of
this is
numbers.
E to the stuff. Okay,
That's funny.
and this is for
Bullshit.
so when T equals 0, what do you get?
Time is 0.
1 or
Yeah,
0.
this
Zero,
becomes,
yeah,
this
zero.
becomes 1 and this is Q naught. So this is discharging.
Oh, okay.
So this is your initial value, okay? And then it's going to get smaller as T increases. All right? Okay, so this is an exponent. So remember, you guys kept trying to make the graphs exponential, and I said we haven't seen anything exponential yet. This is exponential. This is what exponential looks like mathematically. All right? If you want to figure out the current, well, you just take the time derivative of this. Okay? So it looks pretty much the same, but I naught is going to be Q naught over RC. If you don't believe me, take a derivative. Okay? That means when the capacitor discharges, it looks like this. Okay? We don't really have time to do too much with this. But we'll finish this up on, what is that other day? Thursday?
Something like that.
Wow.
All right.
One of these days.
It is in wine.
What?
It is in wine.
All of them.
Exactly.
But yeah, we're pretty much done. We're going to talk about RC circuits a little bit more. Everything else we do is just on household electricity. Not necessarily something that's going to be on the test, but it's useful to know since you probably live in a house with electricity. So we're going to try this problem. This is mostly just a plug-in kind of problem, just to get sort of warmed up on how you use exponentials. And for instance, why do you think it says the switch has been in this position for a long time?
So
Yeah, that means it's totally charged, right? Because if it's just been flipped, we don't know if it's charged up or not.
Let's start by looking at this problem and the words in this problem. It says the switch in the circuit below has been in position A for a long time. What do you think we mean by a long time? Well, a long time probably implies that it's longer than the amount of time it takes to charge the capacitor. So we can assume capacitor is charged. And this is the situation where this switch is open. So when the switch is open, it looks a lot more like this. We just have this capacitor connected to this battery and it's charging up. Okay, so because it looks like this, we assume the capacitor is charged, and we can figure out from that what its voltage and its charge are. So its voltage is pretty simple. It's going to be the same as this battery over here, and we'll say delta V equals 9 volts at t equals 0 seconds, because now the time matters. Well, if we know that, we can figure out the charge, because we know that C is equal to Q over delta V. Actually, more importantly, this is the definition of what capacitance is. So if we want to figure out Q, that's going to be C delta V. So that's 1 microfarad times 9 volts. Now you can write this as 1 times 10 to the negative 6 farads, but you actually don't need to, because since you know it's going to be 1 times 10 to the negative 6, so it's 1 times 9, you'll end up with 9 times 10 to the negative 6, which is 9 microcoulombs, because remember, farad is coulombs per volt. All right. So your charge initial is 9 coulombs. Your initial voltage at t equals 0 is 9 volts. So now we have these values, and now we can go back to the second situation. So once you flip this switch, now it looks like a standard RC circuit. So at time equals 0, we know that delta V is 9 and our initial charge is 9 microcoulombs. So we can just use our formula for charge over time, which is going to be Q naught E to the negative T over RC. All right, so we can plug in numbers. This is 9 microcoulombs E, because we're looking for 5 microseconds. Now I just want to separately write out what RC is. So RC, which is tau, that's the time constant that we were talking about. RC is going to be equal to 10 ohms times, it's 1 microfarad. So this gives us 10 micro somethings, and it turns out ohms times farads gives you seconds. I know that's an annoying thing, but that means tau, our time constant, is about 10 microseconds, which means in 10 microseconds, this thing should be just about, it's not discharged, but it's mostly discharged. Okay, so it only takes a few time constants to totally discharge this thing, but since this is an exponential, it drops pretty quickly. So you would end up having negative t, which is 5 microseconds, over 10 microseconds. Well, what's 5 over 10? These have the same units. That's 1/2. So we end up with e to the 1/2. So we end up with 9 microcoulombs times e to the 1/2. And that gives us something along the lines of 5.5 microcoulombs. So Q at 5 microseconds is going to be 5.5 microcoulombs. Now we have to ask ourselves, did this make sense? Well, yeah, this is only about half of our time constant. So does that make sense? Yeah, this is only about half of our time constant, so we're not expecting this thing to be totally discharged. If it's the whole time constant, it's going to be a lot closer to being totally discharged, but we've only gone about 5 microseconds out of the 10. Now, it's not exactly totally discharged, it's just the time when your time constant just gives you 1 over e as your value, but remember 1 over e is gotten pretty small. So that's the answer to the first part. And then if you want to figure out the current, you just have to do this again. So you can either use the formula, which is just the derivative of this formula. So when you take the derivative of this formula, don't take the derivative here, that's going to give you 0. Take the derivative of the original formula, that's going to give you I is equal to Q naught over RC e to the negative t over RC. Well, you'll see this part right here is the same thing. That's 5.5 microcoulombs. So you just have 5.5 microcoulombs divided by RC, which is 10 microseconds, the micros are going to go away. They're both 10 to the negative 6. You get 5.5 over 10, which is 0.55 amps, or 550 milliamps. All right. So now, just using this math, we figured out both the current at 5 microseconds and the charge at 5 microseconds. And we also know a little bit about the time constant and what it does. So after about 5 microseconds, you get this and this.
Okay, so if we have a completely discharged capacitor and this switch closes, I want you to think about what's going on in this circuit. Okay, let's say this is our battery. We have a resistor. What's the initial potential difference across the capacitor? It's going to be 0. Okay, so what determines our initial current? Battery and the resistor, right? We just use V equals IR. So whatever the voltage is of this divided by the resistance, that should give us our initial current. Just our initial current. Because what happens as the current starts to flow? This thing charges up, right? So that means now, instead of all the voltage dropping across the resistor, it has to start splitting. Some of it drops across the resistor, some of it drops across the capacitor. So let's say this is a 9-volt battery. Initially, 9 volts drop across the resistor. This thing 0 comes right back. As this starts charging up, now it has a potential. Let's say that it now has built up a potential of 1 volt. Okay? That means that this thing has 9 volts, this thing has 8 volts, and this thing has 1 volt. Okay? So as this thing starts to charge up, less and less voltage drops across the battery. So what's happening to the current? Is it getting bigger or smaller?
Staying the same. It's not doing anything. It's not dropping. Shouldn't we say the same?
The resistance stays the same, but look, if the voltage is getting smaller across the resistor, right, that means the current has to be going down. Because as you charge up the capacitor, it's going to slow down the flow of current from the battery. Because remember, when this capacitor is totally charged, what's the current going to be? 0. Okay? And what voltage is this capacitor going to charge to?
Whatever the voltage of the battery.
Whatever the voltage of the battery is. And you're like, well, what about this resistor? Well, it doesn't matter what the resistance is once your current goes down to 0. Okay? Because once your current is 0, it's like this resistor doesn't exist. Resistors only have a voltage when there's a current. V equals IR, Ohm's law. Okay? So you start out with 0 voltage across the capacitor. Okay? You end up with the voltage of the battery, no matter what the resistor is. Okay? You start out with a maximum current based on just the battery and the resistor. You end up with 0 current. Okay? So what's happening to the charge? What does it start at?
0.
0. What should it end at? It'll depend on the battery and the capacitance, right? So you'll end up with the same charge you would start with if you were discharging. That's what you would expect, right? So you start with 0 charge, you end up with your max charge based on these two things, okay? Your initial current is based on these two things, okay? All right. So what does this look like? Well, the current equation looks exactly the same, okay? Your current still looks like initial current e to the tau, t over RC. But your charge looks a little bit different, okay? Because you want to start with a charge of 0, all right? So if t is 0, what's e to the 0?
1.
1. Okay? So then you have 1 minus 1. Yeah, that's 0. And then this looks like this, right? So you end up at this Q max. It's asymptotic, but like we said before, charge isn't continuous, so at some point this is considered it's fully charged. It's probably about 3 times tau. okay? So the other way you can figure out that the current looks the same, how do we get the current from a charge equation?
Divided by RC.
Kind of.
Initial charge divided by RC.
You just take the time derivative, right? You take the time derivative of this term, this one term, goes away, okay? And you just end up with I naught e to the negative t over tau. Okay, so you can think about how we get current both intuitively, you can also get the same thing mathematically, and that's good because usually in physics, no matter how you end up reasoning something out, you should get the same answer. Okay, so this is how charging works. This is how discharging works, and this is current for both of them. Okay, so no matter what, charging or discharging, you start with a large current, and the current goes to 0. Okay. Any questions about this? All right, let's find out. All right. Cool. Let's discuss this. We'll do it again. Take a little longer, maybe. Okay, better. So, how do we calculate the time constant?
RC.
RC. So what's R?
4.
2 plus 2. Why?
Because it's in series.
You have two resistors in series. They both count. Okay? So when we have resistors in series, how do we add them?
Straight up.
Just
Straight
add
up.
them. So 2 plus 2 equals 4. Okay? So our resistance, our equivalent resistance, our total resistance is 4 ohms. Okay? What's our capacitance?
1 farad.
1 farad. What's 1 times 4?
4.
4 seconds. Okay? So remember, if you have a larger resistor, what does that do to your time constant? Increases it. Think about this. If you're looking at V equals IR, if you increase the resistance, what do you do to the current? It decreases, okay? Because those still have to make up V. So if resistance goes up, current goes down. If current's not flowing as fast, that means you discharge or charge more slowly, which means a longer time constant, okay? Smaller resistor means you can get current flowing faster. That means a short time constant, okay?
It's like traffic.
Yeah. The other thing is in the time constant is the capacitor. If the capacitor stores a lot of charge, if it's a big capacitance, then it's going to take longer to get rid of all that charge, okay? If it can't store very much charge, it should be easy to get rid of all that charge relatively quickly. So that's how R and C work together to determine the time constant. If you have a big capacitor that stores a lot of charge, right, that takes longer to discharge. If you don't have a very high current because you have a high resistance, that's going to take longer to discharge. Okay? All right. So